Right now, you're probably watching this on a device with billions of transistors switching on and off millions of times per second. Yet somehow, you just clicked a button. You didn't have to think about electrons, logic gates, or machine code. This is the magic of abstraction. In computer science, abstraction is the art of hiding complexity. It's about creating layers where each level provides a simpler interface to the messy details below. Think of it like driving a car. You turn a steering wheel, you don't need to understand the hydraulics, the rack and pinion system, or the tire mechanics. That's abstraction. But in computing, we don't just have two layers, we have dozens. Every time you send an email, tap a screen, or stream a video, you're standing at the top of an incredibly tall ladder. Let's climb down and see what's underneath. At the foundation, we have pure physics, transistors, tiny switches made from silicon, flipping between on and off states. This is where the abstract meets the real world. Most transistors today are MOSFETs, which stands for metal oxide semiconductor field effect transistors. A MOSFET has three terminals: the source, the drain, and the gate. When you apply a certain level of voltage to the gate, then only current can pass, which exactly works like a switch. Billions of these switches, each just nanometers wide, working together. At the next level, we have logic gates. By combining transistors, we can build logical operations. For example, let's take the OR gate. An OR gate outputs true when at least one of its inputs is true. We can build this behavior by connecting transistors in a specific arrangement. As circuits grow more complex, it becomes messy to think about each transistor individually, so we abstract further, giving each combination a simple symbol to represent its function. Combine enough gates and you get something remarkable: a processor, arithmetic logic units that do math, registers that hold data, memory that stores information. This is computer architecture. Engineers design these systems without worrying about individual gates. That complexity is hidden below. Now we reach the first layer of software, machine code. These are the raw instructions that processors understand. Binary sequences like this, cryptic, precise, and incredibly tedious to write. This is what the hardware actually executes. To make life easier, we invented assembly language. Instead of remembering that string of ones and zeros, we just write simple mnemonics like MOV. Same instructions, human-readable names. It's still one-to-one with machine code, but our brains can actually handle it. But assembly is still exhausting, so we created high-level languages: C, Python, JavaScript, Java. Here, one line of code might translate to dozens of assembly instructions. You write, print this string, and the language handles all the complexity underneath. Different languages offer different abstractions. Some prioritize speed, others prioritize ease of use, but they all serve the same purpose: hiding the complexity below. Of course, computers don't understand these high-level languages directly. That's where compilers and interpreters come in. A compiler translates your entire program into machine code before it runs. An interpreter reads and executes your code line by line. They bridge the gap between human logic and silicon instructions. We go even higher. Libraries and frameworks let you do complex tasks with simple commands. Want to process images? Import a library, build a website, use a framework. Someone else wrote thousands of lines of code, and you access it all with a few words. Another layer of abstraction. Between your programs and the hardware sits the operating system, the great mediator. It manages memory, schedules processes, handles input and output, and lets multiple programs share the same hardware without chaos. You never have to think about allocating CPU cycles or managing drivers. The OS abstracts that away for you. Finally, we reach applications, the top of the ladder, the place where most people live. Click, drag, type, tap. All that complexity, from transistors to frameworks, compressed into intuitive interfaces.